Hello everyone. In today's video, we're going to begin our discussion on a new unit, electrostatics. First, we're going to start by going over what is electrostatics. So, if we break down the word, we see electro means having electricity, which comes from the Greek word for amber. Now, why amber? It's because amber, if you did not know, really builds up static electricity really easily. So, if you know that static cling that you get, either sometimes your clothes gets it, or for me personally, I like fruit roll-ups a lot. Generally, have them for lunch. When you peel the fruit roll-up off the wrapper, it gets all like it sticks to you, has that static cling. Amber gets that very easily, and that was the first time it was really noticed. So the Greeks named the word after amber because that's what caused it. Now, static here means not moving. So in this unit, we're going to be focusing on charges that either are staying put into one object or maybe moving from one object to the other and then staying put. The next unit that we're going to get into is electricity, where we have charges that are constantly moving from one place to the other to make things like light bulbs work and stuff. So static electricity is a study of electricity and charges that are not moving. So, charge. Electrons and protons possess a property called charge, just like they possess a property called mass. Electrons have something that we refer to as negative charge, and protons have positive charge. They are the same magnitude as each other, which means that they're equal in strength, but but they're opposite in their pole. Neutrons are neutral and they have no charge. So when we look up at an atom, we have the positively charged protons in the nucleus, and then the negatively charged electrons floating around, and then the neutrally charged neutrons also in the center as well. Now, how charges interact will be a big focus on this unit. Charges will apply forces on other charges. Now, this is something that we've learned in chemistry. We're pretty familiar with it. But just to go over the basics again, like charges repel each other. So if we have two negative charges, they will push each other apart. If we have two positive charges, they will push each other apart. If we have a positive and a negative charge, they will attract to each other. So just like magnets, where we have the opposites attract and the like things repel, it works the same way with charges as well. Now, atoms, we can have different types of atoms. A neutral atom, which is the most common way we find atoms, they contain equal number of protons and electrons. Most atoms in the universe follow this rule. However, during some chemical reactions, we can get positively charged atoms or negatively charged atoms. Now, the big thing to note here is the thing that changes is the electrons. So the protons of an atom will always stay put. They have an enormous amount of weight in comparison to the electrons, so they won't be the thing that moves around when we discuss charges that move. It's the electron that moves. So a positively charged atom isn't an atom that gained some protons. It's an atom that lost electrons. And same with a negatively charged atom is an atom that gained electrons. So it's the electrons that move from one place to another. Now, this is all well and good, but in physics, we're going to be focusing on the macroscopic events. So what's actually happening to real world size objects like you or that the fruit roll-up wrapper that statically cling to you. What's causing that to happen? Well, that's something we refer to as net charge, which is the overall buildup of charges inside of an object. So all objects are made up of atoms. We know that by now. But when an object has more positive charges than negative charges, it itself becomes positively charged. And an object that contains more negative charges become negatively charged. It all makes sense. So over here we have a image of some kind of macroscopic object. And you can see that this is a positively charged object because if you look at the number of protons, there's two for each atom, and the number of electrons, there's only one here and one here. There's more positive charges than there are negatively charges. So that object is going to act as a positively charged object. Now, why this is important is to circle back to the forces, where positively charged objects enact a force on other charged objects. And that's where this comes from. One other thing that's important to note is a new conservation law. So we've talked about conservation of mass, we've talked about conservation of energy, we've talked about conservation of momentum this year. Now, this is something you've talked about in chemistry, but we're bringing it back, and that's conservation of charge. So just like all the other things, you cannot create nor destroy charge. You can only move them around. So if you were to make a positively charged object, you would make another object negatively charged by the same amount. Now, we have two different types of objects that we're going to be focused on when it comes to charges. We have conductors, where electrons are relatively free to move, which means it's easy to either give electrons to this object or take electrons away from this object. But also, when you do it, the charge will spread throughout the entire object. These are things like metals or electrolytes, which are things that, when dissolved in water, conduct electricity quite well, like salts. And then we have our insulators, where the electrons, it's hard to get the electrons to move. Now, you can still make insulators into charged objects. In fact, we often notice charged objects on insulators more often than we do on conductors. For example, the static cling in your clothes or the static cling of that fruit roll-up wrapper, all those things are insulators. What makes them different than conductors is the fact that they hold on to their charges much more, and they also tend to hold it on to a very localized position. So one classic thing that we do is we take balloons and rub it against your hair. If you do that, that balloon will become negatively charged. It'll take some of the charges away from you. But only that one area of the balloon becomes charged. So you can take that balloon and stick it to a wall because that one area is filled with charges, but the rest of it is relatively neutral. A can, on the other hand, or something that's metal, does not do that. The charge will spread around it, and if someone was to touch the can in an area, all the charge will probably leave the can into that person. You get a little zap. But for the balloon, you can touch the backside of the balloon and you won't hear any shocks or crackles or anything like that, because that part of the balloon is neutral, and it's only the part that you really charged up that has a negative charge. If you were to feel your hand around the part that you charged up, you would hear and probably feel little bits of little tiny shocks as you're allowing these electrons to pass back into you. So that's the difference between conductors and insulators. Now, we're going to end today's video just talking about the fact that neutral objects can also be attracted to charged objects. Now, this is different than what most people expect. Most people would assume that only opposites attract. But when we notice things like that balloon example, if I take a balloon and shake it across my head, that balloon is negatively charged. But if I stick it to a wall, it sticks, but the wall is neutrally charged. Why does that happen? And also that fruit roll-up wrapper, when you pull off the thing, why does it stick to your hand? Yes, it must be charged somehow, but you should be neutrally charged. So why does it stick to your hand? Well, this is what we're going to look at in a series of labs coming up. So I'm going to stop talking here, and we will do those labs shortly. Have a good one, everyone.